All right, so we're going to move on to force and Newton's first law and work and energy. And yeah, we'll get into all that. Okay, so here's a question. Who's the one that really started this conversation about motion and force and how things move, and if you like push or pull them, then they move more or less, or what's going on? So who's the person who came up with this? He's pretty important. You may have heard of him. His name's Sir Isaac Newton. And he's pretty much the most influential scientist of all time, or at least one of them. And he's definitely a key figure in the scientific revolution. So his biggest work was on gravity and the laws of motion and force. He did a bunch of other stuff though. And really cool, fun fact, he came up with the laws of gravity when he had to stay home from university because of a pandemic. So, kind of interesting considering the times we're in right now. So anyways, what did he say about work and all this stuff? So he actually came up with 3 laws of motion. So first we're just going to go over the first one because, that makes sense. And that is, you've probably heard it, an object at rest stays at rest, and an object in motion stays in motion with same speed, same direction, unless acted upon by an unbalanced force. Okay, so again, object at rest stays at rest, and unless acted upon by an unbalanced force. Sometimes it says an outside force, but really an unbalanced force is the most important thing there. Or if it's in motion, it stays in motion, same speed, same direction, unless acted upon by an unbalanced force. So this is called the law of inertia. And inertia is just that. It's the tendency of an object to either do nothing if it's already doing nothing, or if it's going one way, just to keep going that one way. This is a tendency of an object to remain unchanged and just keep going on its trajectory. But at the same time, we do know that that's not fully true, at least on Earth, because we're like, well, no, an object doesn't stay in motion. That's in motion doesn't stay in motion. We always see stuff stop. Like, for example, kick a soccer ball, it's going to eventually stop rolling. And why is that? Well, that's because it actually is being acted upon by an unbalanced force. So that's the key part of it. If it's not being acted on by an unbalanced force, if there was no friction here, then it would just keep going on forever. And that's why things in space do that. They just keep going. They don't have any unbalanced forces there. So if you push something in space, it will just keep going forever. Have that in the law of inertia. So remember, on Earth, we do have these unbalanced forces all the time, okay? And so with the soccer ball, that's called friction. So of course, objects at rest don't move because all forces acting on it are balanced, right? And sometimes you can even like put a force on something and it still won't move, and that's just because the force that's opposing you is still equal and opposite, okay? So something like this, either there's no forces working or there's perfectly balanced forces working if it's an object at rest. So by the way, when you draw an arrow to indicate force, the size is very important, okay? If I have 10 newtons here on the left and I have 10 newtons here on the right, the arrows should be about the same size, okay? And then, of course, when we have objects in motion, that's because we have unbalanced forces, okay? So the force in one direction is going to be greater than the force moving in an opposite direction. So this is the soccer ball, right? So we know that if a soccer ball is kicked, it has a much bigger force in this direction, and then we have a force of friction moving in that direction. So it's still moving forward, but it is slowing down. But of course, the objects will always move in the direction of the bigger force. So in this case, with the tennis ball here, which direction is it going to move? Well, to the right, because the right going arrow is bigger than the left one. Okay, so it's going to move to the right. It has an overall force of 5 newtons to the right. Woohoo, look at that. So what is a force? I've been saying that word a lot. It's really just a push or a pull. That's all a force is. It's something that pushes or pulls an object, and it's measured in something we call newtons because the units are crazy, okay? But that's all you need to know about a force right now. It's a push or a pull in a certain direction. And then we can calculate force using this equation here. So we have force is equal to mass times acceleration, okay? Really, really important here. When we are working with this, we need very specific units, okay? Mass needs to be in kilograms, not grams. Acceleration needs to be in meters per second squared. So when you multiply those together, you get this weird thing for force, which is just ridiculous. So they're like, instead of having this weird Mod Podge of units, we're just going to make a new unit and call it newtons. Okay? So here again, F is force, M is mass, and A is acceleration. And so the units of force should just be newtons, because kilograms times meters per second squared just starts getting a little bit too ridiculous. Okay? So remember, that's what 1 newton is equal to. Okay, but instead of having that big mess of units, they're like, okay, well, we're just going to name that after the guy that came up with all this stuff. And we now call it a newton. Okay? And that's Newton's second law, actually. So many people, when I ask them, what's Newton's second law, in my physics classes, and they like think and they think and they think, they're like, why can't I think of any wording for Newton's second law? And I said, because it's an equation. It's just that force is equal to mass times acceleration. All right, so let's get onto an example here. So we have a 5,000 gram toy car. Stop, write down what you have. So we just found out our mass is 5,000 grams. Now, one question is, grams acceptable? Let's go back here. What did we want mass in? Oh, we wanted mass in kilograms. So this is not okay. So we need to convert this to kilograms. So I'm going to use my factor label method. So remember, that is, I want to cancel out the units that I no longer want. So I should probably put grams on the bottom there, so then these can cancel out. And I want kilograms. So what do I got to do? Then I have to figure out the relationship between kilograms and grams. Does anybody know how many grams are in a kilogram? If you don't, it's 1,000. Kilo always means 1,000. So for every 1 kilogram, I have 1,000 grams. Okay? So really all I have to do here is divide 5,000 by 1,000, and I get 5.0 kilograms. Okay, perfect. Let's move on. It's accelerating at 6.0 meters per second squared. Okay, perfect. What is the total force applied on the car? Well, force is equal to mass times acceleration. Okay, so my mass was 5 kilograms. My acceleration is 6.0 times, or meters per second squared. Okay, good. So all I have to do is multiply 5 and 6. What's 5 times 6? That is 30. So first of all, let's make sure we have the right number of significant digits. This guy had 4 significant digits. This guy had 2. Okay, so therefore, my answer needs 2. Perfect, it has that. It needs units. There we go. And technically it needs direction, but it doesn't give us a direction in the question, so we good, I think. Perfect, there we go, that's it. There's our force. So now we're going to move on to something called work, which no, it's not quite what you think it is. So there's, you know, like real life work where it's like, I'm doing work right now because I'm like making a lesson and teaching you. And then there's work in physics, and it's a little bit different, okay? So, oh, look at that kitty. Yeah, she ready. I'm going to do some work. Did I do it? Did I nail it? I nailed it. So work is defined as energy transferred to an object when force is applied that causes the object to move, okay? You apply a force, the thing moves, you've done work. Maybe. So there's one really, really important thing though. Okay? So, but first of all, work has to do with applying a force and then the object that you're applying a force to being displaced, moving, okay? But three conditions. There has to be a force, okay? So there's no work done if you're just like coasting on your bike. If you're not actually like pedaling, then you're not doing any work, because then when you're just coasting, there's no force there. The object has to move its position, okay, in order for work to be done. So if I push on my table that I'm doing this at right now, but I don't push hard enough, it's not going to work. Sorry, it's not going to move. So therefore, I'm not doing work, even though I'm pushing it, but it's not moving right now. And I know you can't see me, so it's more difficult, but I promise I'm pushing the table. Okay? So it has to move position, but most importantly, oh my goodness, object has to move in the same direction as the force. Yeah. So therefore, if I move my table, so this object, this is my table that I'm like working at right now. If I direct it, the force that way, and then it moves that way, I have done work. So you hear that scraping? That's me moving my table. There we go. This cute little kitty right here, guess what? If it pushes up on these barbells, which way is it going to move up? Or which way is it going to move? It's going to move up. So this kitty is going to do work on these barbells. Okay? And now you're going, but sometimes we apply, shouldn't we always apply forces and then it moves that way? No, it is definitely not that simple. Okay? So for example, here you're moving a box, you're pushing a box. So you're pushing it to the right and it moves to the right. So has work been done? Yes, it absolutely has. Okay? All right, so next, say you're walking, which, hopefully something you do every day. Hopefully. Oh my goodness, please walk every day. What's happening is you are applying force upwards against the floor, yet you're moving horizontally. So if your force is upwards, but your direction of motion is horizontal, are you doing work? No, I'm sorry to say you're not doing work. So walking is not work. FYI. All right, lifting groceries. Let's talk about that. So when you're lifting groceries, you're applying a force upwards, right? You're pushing them upwards. And then, of course, the motion is upwards. So you are absolutely doing work here. Look at that. Yes, you're doing work. But then you start carrying the groceries inside. What's going on? You're still applying that upwards force on the groceries. That's why they're not falling down, right? If you stopped applying that force, they'd fall back down to the ground. Yet now the groceries are moving which direction? They're not moving up and down anymore. They're moving horizontally. So are you doing work? You absolutely are not. No. Okay? So that's what's so important about work is, okay, there's got to be force, there's got to be displacement, and they got to be in the same direction. So, of course, in physics, we're all about calculating stuff. Okay, you guys? It's all about calculations. So here is how we are going to calculate work. Work is equal to force times displacement. Okay? Now, work is now a new unit. It's joules. Okay? Because, again, we already knew that force, so F is force, is in newtons, which is like this kilograms, meters per second squared. And then you multiply it by meters again. So it's just a big mess, right? If we want to do joules, so we just are like, no. Okay, so then we just named it joules, okay? After another famous scientist. So that is the unit for work. Okay, so remember, work is in joules, force is in newtons, distance is still in meters, and that's not going to change. So let's do a question where we have to calculate the work being done. A student applies a force of 100 newtons to pull a heavy block 35.0 meters across the flat floor. How much work was done? Okay, let's write down what we have. We have force. Got that was 100 newtons. They're pulling it 35.0 meters across the floor, so that would be the distance or displacement. They're the same thing in this situation. Oh, look at that. So we got everything. If we want to calculate work, which is force times displacement, oh, we got it. So force is 100 newtons. Displacement is 35.0 meters. What's 100 times 35? That is 350. Let's make sure we know what significant digits we need. Here we have 3 with the 100. Here we have 3 with the 35.0. So we're good here with 3 significant digits. And our units are joules. Okay? Now, you might be asking, Miss Waters, do we need a direction here? And yes, we don't, because guess what? Work is a scalar. So there needs to be no direction with work. It is a scalar, which is so super duper awesome. Okay? Let's do one more with work. So now you're pushing a box filled with books across the floor. You have 322.5 joules of work. Okay, so now it's giving us how much work has been done. So that's 322.5 joules. By pushing the box a distance of 4.3 meters. So there we go. We got our distance. Okay, so I want to know the amount of force we exerted. Okay, let's look at this equation again. It's work equals force times displacement. So here we have the work, we have the displacement, but we want the force. So again, I like to rearrange first, but I know a lot of people don't like to do that. So let's plug in the numbers first. So it'll look something like that when we plug in the numbers. And so what we see is that we need force to be all by itself. And right now it's being multiplied by 4.3. So what's the opposite of multiplying by 4.3? It's dividing. Okay, so we need to divide that side by 4.3 to cancel it out. And then we need to do the same thing here where we divide the side by 4.3. Okay, so when we do that, I'm just going to put force on this side. We get that force is equal to 75. And what are the units for force? Newtons. And let's make sure we have the right significant digits. We got 4 there, we got 2 there. So, it looks like we need 2 because we always need the least amount. Okay. So that wasn't so bad, was it? Really, these equations are actually pretty nice to rearrange. You have no denominator, so you don't have to worry about doing that. So really, if you need to solve for force or displacement, you just divide both sides by the other one, right? So it's actually a pretty nice equation to have to rearrange. Finally, I'm just going to go over one more thing. And we're definitely not going to be done with energy, but I can't talk about work without talking about energy. Because again, it's a word you've heard a lot, but remember, this might not be the same as what we talk about in real life. Energy defined by physics might be a little bit different, but sometimes actually it's the exact same. So energy is the ability to do work, okay? So it's the ability to exert a force that will provide a displacement. That's what energy is. It's measured in joules as well, okay? So obviously it and work are very closely tied. At this point, we're going to assume there's no loss of energy during a transfer of one energy to another, which is a big assumption, but that's what we're going to do just to get you guys used to energy for Science 10, okay? And so all we know is that change in energy, remember this thing right here means change in. So we're just assuming that there's no loss of energy when we change energies, okay? So change in energy is equal to work being done. So for example, I'm not pushing the table, and then I'm pushing the table and it's moving. There was a change in energy there where I went from having no energy to having energy or exerting energy onto the table. Gotta move it back. But here's some good news for you. Work and energy are scalar. You don't have to worry about direction with those guys. So let's just do one more example. So we have a champion weightlifter doing 6,000 joules of work. Okay, let's write that down. So work, we got 6,000 joules. Lots of work being done. When lifting a barbell a height of 1.8 meters, so there's our distance, 1.8 meters. Okay, so we want to know how much force the lifter exerts on the barbell. Okay, well, this looks a lot like the one that we just did. So we know work is equal to force times displacement. Let's plug in our numbers. 6,000 joules is equal to force times 1.8 meters. And of course, to get force by itself, I have to divide both sides by 1.8. That cancels that out there. And I get that force is equal to, so what I get here is 3,333.3 continuing, and that's newtons. But of course, that definitely is not to the correct number of significant digits, because if you look here, we have 4 there, and we only have 2 there. So I need this in 2 significant digits. Uh-oh. How do I express 3,333 in 2 significant digits? I'm going to need to use scientific notation here. Okay, so I'm going to take this decimal, I'm going to move it up 1, 2, 3 times. Okay, so we're going to have 3 point, and then I only want 2 significant digits, so I can only have one number after the decimal, and that's going to be a 3. Because of course we're not going to round that up because the next number is also a 3. And so that'll be times 10 to the 3 newtons because we moved the decimal 3 times. There we go. So make sure you pay attention to that because sometimes those significant digits will bite you in the butt, okay? So that's the first example, and then it says how much energy is gained by the barbell. Well, keep in mind this is actually easier than you think. What do we know about energy? We know that work is equal to the change in energy. So first the barbell had 0 joules of energy probably because it was just sitting there, and then it was lifted with 6,000 joules of work. So it gained 6,000 joules of energy. So it's not always calculation. Sometimes it is just as simple as saying, oh, well, there was 6,000 joules of work done on it, so therefore it gained 6,000 joules of energy. Okay? So just to review, when you do work on an object, you give that object energy. It now has energy because, of course, when you lift something, you've just given it the potential to fall back down. So that is energy. The greater the force you apply, the longer distance you move objects, then the more energy you expend, so the more work you did. So, of course, energy and work are both measured in joules. Okay, so work and energy are kind of weird because it's really not just the units that are the same. The two terms can be interchangeable. Okay, but it's just really important that you note that work is the same as a change in energy, not necessarily energy itself. So when you expend energy to do work, and you do work on an object, you give it energy. So they're kind of very symbiotic like that. They are kind of interchangeable. Okay, so work is the amount of energy given to an object, and that is, of course, just exerting a force over time. So really, we can even say that change in energy is force times displacement as well. Okay, so work and energy are very, very closely related. We're going to be talking a lot more about energy. That's actually going to be the next few lessons here, and it's going to be really, really important. Okay, so it's just really important at this point that you understand this relationship between work and energy. Go do some work on these, kinds of problems and questions. And I know it's a little bit overwhelming at first, but the more you do, the more you understand it. Okay? Good luck.